Welcome to This Explainer. Today, we're taking a leap. Literally, we're going to leap right off those flat, two-dimensional screens we're so used to staring at and expand out into the physical, three-dimensional world that we actually live in. And honestly, the best part? We're going to see exactly how mathematics manages to capture our physical reality using something called sets. It's an absolutely brilliant concept, and I'm super eager to explore it with you.
Okay, let's dive right in. We're all pretty familiar with standard graphs, right? You've got an x-axis, a y-axis, you plot a point on a map, or maybe a flat tabletop, and you know exactly where it sits on that surface. That's your standard ordered pair. But my question for you today is this. Have you ever encountered an ordered triplet? Like, have you ever seen math that totally breaks free from the flat page and moves beyond just the standard x and y axes?
To really see why we even need this, let's get physical for a second. I want you to literally point your finger at a specific spot on the flat screen you're looking at right now. Go ahead. That spot is easily defined by an x and y coordinate. It's completely trapped in two dimensions. But now, point to a spot floating in the empty air in front of you, like where a mosquito might be hovering halfway between you and the screen. How do we mathematically trap that mosquito? That hovering point just cannot be mapped with two numbers. We need a totally new tool.
Section 1. Stepping into 3D space.
So the upgrade here is beautifully simple. An ordered pair, like 3, 1, locates a point on a perfectly flat plane. Think of a city grid. But to find our hovering mosquito, we just add a third axis, a perpendicular z-axis. This gives us our ordered triplet. For example, 3, 1, 2. Boom! We've just expanded our mathematical universe from a flat sheet of paper to the entire physical volume of a room. Let's make this super concrete. Imagine you're standing in the corner of a totally empty room. The x-axis is the wall running to your left and right. The y-axis, that's the vertical line running straight up from the floor to the ceiling. And the z-axis is the depth. It runs forward and backward, straight out into the middle of the room. So, if we have that ordered triplet 3, 1, 2, what does it actually mean in real life? It means we take 3 steps right along the x-axis, we move 1 unit straight up the y-axis, and then we step 2 units forward into the room along the z-axis. With just those 3 simple directions, we can map absolutely any specific point in the 3D world around us.
Moving on to Section 2, multiplying 3 sets.
Now, these ordered triplets don't just magically appear out of thin air, right? They're actually formed by a process called the Cartesian product. You've probably seen this used with 2 sets to make pairs, but here we're applying it to 3 sets, p times q times r. So the crucial point to remember is this. You must take one element from the first set, p, then one from the second set, q, and finally one from the third set, r. You have to do it strictly in that order, because if you mix up the order, you literally end up at a completely wrong point in space.
Okay, let's look at a real example using 3 totally different sets. Set P contains the numbers 1 and 2. Set Q is filled with the letters A, B, and C, and set R has 2 Greek symbols, beta and theta. Our goal here is to multiply P, Q, and R together.
So how do we build this? Well, we just trace the logical flow. We start with the first element of P, which is 1. We pair it with the first element of Q, which is A, and we finish it with the first element of R, beta. So our very first ordered triplet is 1, A, beta. But hold on, we aren't done with 1 and A just yet. We can swap that last element to theta, giving us 1, A, theta. Then we step to the next letter in set Q, giving us 1, B, beta. You basically just methodically build this out, picking one element sequentially from each set until you've exhausted every possible path, ending all the way down at 2, C, theta. It's a little tedious, I'll be completely honest, but if you put all these combinations into one big set separated by commas, you've successfully created the full Cartesian product of P, Q, and R.
Which brings us to Section 3, building the combinations.
But here's a fun question. What happens if, instead of 3 completely different sets, we challenge ourselves to multiply the exact same set by itself 3 times? We're looking for p times p times p. And set p is incredibly simple. It literally just contains the numbers 1 and 2. Sounds easy, right? But mapping out these spatial combinations in your head can actually get super confusing really fast, mainly because all the numbers look exactly the same.
To keep from pulling our hair out, let's use a clever little trick. We're going to color code the sets. We'll assign the color blue to our first P, green to our second P, and yellow to our third P. This trick is a lifesaver because it helps our brain visually organize the repeating 1s and 2s so we never lose our place floating around in that 3D space.
Check out how the colors act like a roadmap through the 8 possible combinations. We start with blue 1, green 1, yellow 1. Then we swap the end. Blue 1, green 1, yellow 2. Next, we change the middle position. Blue 1, green 2, yellow 1, and so on. By holding the first number steady and systematically changing the later ones, the color method keeps our ordered triplets perfectly, beautifully organized. We've cleanly mapped out the entire Cartesian product of p times p times p without skipping a single coordinate.
All right, the final stretch. Section 4, Mapping the Infinite Universe.
Up to this point, our sets have been kind of small, right? 2 or 3 items, but let's scale way up to a massive set, the set of all real numbers, designated by a capital R. I want you to imagine every single number imaginable, positives, negatives, fractions, decimals, stretching out infinitely in both directions. Mathematically, R is represented as a single, continuous, one-dimensional number line. Just think of a ruler stretching out endlessly to the left and the right.
Now watch what happens when we unleash our Cartesian product tool on this. If we take that infinite ruler R and multiply it by another infinite set R, we generate every single possible point on a two-dimensional plane. Think of a limitless sheet of ice or an endless tabletop stretching out forever. That massive expanse, that is mapped perfectly by R times R.
So, knowing that R is a line and R times R is a flat infinite plane, I want you to just pause for a second and synthesize everything we've talked about today. What does R times R times R actually mean? What happens when we take that flat, endless tabletop and multiply it by a third, infinite, perpendicular z-axis?
Here is the absolute mind-bending realization. R times R, which is often written as R cubed, literally represents our entire three-dimensional reality. It encompasses every single microscopic point in the infinite 3D universe around us. By just picking an X, a Y, and a Z from the infinite set of real numbers, we can mathematically pinpoint the exact location of a star in a distant galaxy or, the very tip of your nose right now.
And this brilliantly illustrates why advanced math notation looks the way it does. Whenever you see these symbols, they aren't just random letters and numbers meant to confuse you. R squared is simply shorthand for the massive Cartesian product that makes up our entire 2D flat space. And R cubed? That's the shorthand for the infinite sets that define actual 3D physical space we breathe, walk, and live in every single day.
We've gone from simple little pairs on a flat page all the way to mapping the entire known physical universe using ordered triplets. But before I let you go, I want to leave you with a spatial puzzle to twist your brain a bit. If R squared maps the flat 2D plane of your screen, and R cubed maps the massive 3D physical space of the room you're sitting in right now, what on earth would R to the power of 4 look like? Think about what it would actually mean to add a fourth perpendicular axis to our reality. It's pretty wild to think about. Thank you so much for exploring these dimensions with me today, and keep questioning the shape of the universe around you.